Okay, welcome to some more CPU scheduling practice. In this, we're going to do first come, first serve, shortest job first, multi-level feedback queue, and preemptive priority. So before we waste any time, let's get started. So let's draw our Gantt chart here. And we're going to start with first come, first serve. Now the difference in this exercise is that instead of just having one CPU burst, what we have is CPU, I/O, CPU. So if you notice here, each process has a CPU burst, then goes to I/O, then has another CPU burst. So this is a very good exercise because it gives you the opportunity to have a bunch of different processes arriving at all different times. So let's get started. So if we start at time 0, we're going to have to take into consideration the arrival time, and since this is first come, first serve, that's really all we need to take into consideration. This is also non-preemptive, which means that once a process gets on the CPU, it will remain on the CPU until it completes its current CPU burst. So at time 0, we have P1, and P1 has a CPU burst of 5. So P1 will be on the CPU for 5 time units, and it will then complete its 5 time unit CPU burst, and it will go out to I/O for 6 time units, and then it will come back from I/O after 6 time units, and it will have a new arrival time into the ready queue at time 11. Now the current time is 5, and so the next one to, again, this is just first come, first serve, so the next one to arrive was P2 that arrived at time 3. So P2 will go for 4 time units until time 9, and then it will complete its CPU burst. It will go out to I/O for 2 time units and will then come back into the ready queue at time 11. So you will notice that at time 11 we will have the arrival of both P1 and P2. So we'll have to break that tie. I'm going to break that tie by process number, and that's the way I break it also on my on the program assignment. However, there's no wrong answer. If P2 happens, if you put P2 before P1 because they both arrived at time 11, it'll just change the end result slightly. So now the current time is 9, and the next one to arrive was at time 4 was P3. So we have P3, which has a CPU burst of 2. We'll go until time 11. We'll be done. We'll go out to I/O for 3 time units. So P3 will now have a new arrival time at time 14. And the next one will be P4, which will go until time 16. And then we'll go out to I/O for 2 time units, and we'll have a new arrival time of 18. Now, since this is first come, first serve, you need to pay attention here because it's based on the arrival time. So P5 is not going to go yet because P5 arrived at time 14. So really the next one to go would be either P1 or P2, and like I said before, I'm going to choose P1, and P1 will go until time 23 because it has 7 units of CPU burst left, and then at time 23, P1 is done. The next one to go will be P2 because it arrived at time 11, and P2 has a CPU burst of 3 time units, so it will go until time 26, and then P2 is done. Now the current time is 26, and we happen to have P3 that arrived at time 14 and P5 that arrived at time 14. And like I said, I'm going to break those ties by process number, but in reality it could be either one. So I'm going to have P3 go next and finish its CPU burst. It'll be done at time 30. And then we have P5, which will go until time 33, and then go out to I/O for 2 time units and come back at time 35, and P3 was done. And so now we have P4, which will complete its last CPU burst and be done at time 40, and then we have P5, which will complete its last CPU burst and be done at time 44. So the total time for this to run, it took 44 time units. It's 100% CPU utilization. And then you can use, once you get your Gantt chart done, you use your Gantt chart to get the results. So the results, you get the response time, which is from the time of arrival to the first time on the CPU. So P1's response time is 0. P2's response time is going to be 2 time units. P2 arrived at time 3, and it took 2 time units for P2 to get on the CPU. P3's response time is 5. P4's response time is going to be 4. And P5's response time is going to be 16 because P5 arrived at time 14 and did not get on the CPU until time 30. Again, if your ties were broken differently than mine, then you would end up with a little bit different results on your response times and your turnaround times. And the turnaround time, you take the last entry, which here's P1, ended at time 23. That's when P1 is done. And you subtract the arrival time, which was time 0. So the total time that P1 was active in the system was 23 time units. And then to get the wait time, you can just add up all the CPU, I/O, and I/O time and subtract it from the total time active in the system, because keep in mind that each process is either going to be waiting, it's going to either be waiting and accumulating wait time, it's going to be on the CPU using its CPU time, or it's going to be in I/O using I/O time. So those are the 3 places where a process could be. So the total time, or the turnaround time, is equal to the wait time plus the CPU time plus the I/O time. So if you took P1's time and added up its CPU and I/O time, then the total for that is going to be 7 and 6 is 13 and 5 is 18, and you subtract that from the total time it was active in the system, so it waited a total of 5 time units. The other way you could do it is by adding its response time, which was 0, and then remembering that it arrived at time 11, and then it waited when it arrived at time 11 from time 11 until time 16, so it waited a total of 0 plus 5 more time units. Now, I'm not going to fill out this whole chart. The answers are on Blackboard, and I will add the answers to the end of this slideshow. So that's how first come, first serve works. Now let's move on and do shortest job first. So in shortest job first, this is also a non-preemptive algorithm. So therefore, once a process gets on the CPU, it will not relinquish the CPU until it completes its current CPU burst. So we do not have to worry about anything being preemptive. So let's get started. So with shortest job first, we will have at time 0, the only one. Now how this works is you're going to, of those that are in the ready queue, it's priority based on the one that has the shortest CPU burst. But at time 0, the only one in the ready queue is P1. So therefore, we only need to consider P1, and P1 has a CPU burst of 5. So P1 will be on the CPU for 5 time units, and then we'll go out to I/O for 6 time units, and we'll have a new arrival time at 11. So next, the current time is 5, and those that are in the ready queue are P2, got there at time 3, and P3 got there at time 4. So we can only consider P3 and P2 because those are the only 2 that are currently in the ready queue. And of those 2, P3 has the shorter CPU burst, only 2 time units, so P3 will go next until time 7. We'll go out to I/O for 3 time units, so P3 will arrive back in the ready queue at time 10. So next we're going to, the current time is 7. In the ready queue we have P2 and we have P4. They are the only 2 that are in the ready queue, and the one with the shorter CPU burst is P2. So P2 will go until time 11, go out to I/O for 2 time units, and we'll come back into the ready queue at time 13. The current time now is 11. In the ready queue we have P1, which has the 7 time units of CPU burst. We have P3, which has 4 time units of CPU burst, and we have P4, which has 5 time units of CPU burst. So again, since this is shortest job first, we are going to do P3 next. It has the shortest CPU burst, and P3 will go until time 15, at which time P3 has completed its execution. So now the current time is 15. In the ready queue are all of our processes that are left, P1, P2, P4, and P5. And the one that has the shortest CPU burst of those is going to be P2 and P5. So both P2 and P5 have a CPU burst of 3, as you can see here. However, since after you get to the priorities, if you have a tie with priorities, you break those ties by first come, first serve. So if you notice, P2 got into the ready queue at time 13, and P5 got into the ready queue at time 14, so therefore P2 is going to go next. And P2 will be done at time 18, and will no longer be in the ready queue because it will have completed all of its execution. Now the current time is 18, and in the ready queue we have P1, P4, and P5, and P5 has the shortest CPU burst, so P5 will go next until time 21, and then we'll go out to I/O for 2 time units, and we'll come back into the ready queue at time 23. So in the ready queue now, at time 21, we have P1 and we have P4, and P4 finally gets to go until time 25, and then P4 will go out to I/O for 2 time units and come back at time 27. So now the current time is, it goes till time 26, and we'll come back at time 28. Okay, so now the current time is 26, and in the ready queue we have P1, which has 7 time units of CPU burst left, and we have P5, which has 4 time units of CPU burst left. So we're going to have P5 is going to finish at time 30. P5 will then be done. And now the current time is 30, and both P1 and P4 have 7 time units of CPU burst left, but P1 will go first because its arrival time is 11, and P4's arrival time is 28. So P1 goes until time 37, and then P4 goes until time 44. And as you can see, since it's 100% CPU utilization, it takes the same amount of time, 44 time units, to complete all of this. And then once you get your Gantt chart and your Gantt chart is correct, you can use that Gantt chart to get your response times, your wait times, your turnaround times, and calculate the averages. So now let's move on and do multi-level feedback queue. Now multi-level feedback queue is going to be much more complex because what we have to do is we have to, not only do we have a different algorithm depending on what queue they are, but they also will migrate to different queues depending on different behavior. And then when you have lower priorities and higher priorities, they can also be preempted. So this is a little more complex. So let's get started with my nice, neat Gantt chart. All right, so the current time is 0. Now the only thing we have to worry about at the current time 0 would be P1 because it's the only one there. Now what happens if P1 gets on the CPU and gets preempted for time quantum? So let's remember that if you are a Q1, it is a 4 time unit time quantum. If you are a Q2, it's a 7 time unit time quantum. And then if you're a Q3, you just do first come, first serve. If there are any Q2s currently executing, they could be preempted by a Q1. And if there are any Q3s executing, they could be preempted by a Q2 or a Q1. So let's get started. So we start with P1, which has P1's first CPU burst is 5 time units. So P1 is going to go, but it's not going to get to go for its complete 5 time units because it's a Q1 is round robin with a time quantum of 4. So what's going to happen is at time 4, P1 is going to be preempted. So there's a few things that are going to happen. So P1 is going to get preempted and is going to change to a Q2. So P1 is not going to get the opportunity to go again unless there are no Q1s in the ready queue. In addition, P1 has completed 4 of its 5 first CPU bursts, but it has not gone to I/O yet, so we do not mark that out. And it's going to have a new arrival time at time 4 because this is all round robin, is first come, first serve. So now The current time is 4. The current time is 4, and in our ready queue we have P2, P3, and P1. But the truth is that P1 is not even going to get a chance because it's a Q2, so we just need to consider P2 and P3. And since it's round robin, it will be first come, first serve, so P2 would go next. And P2 is a Q1, so P2 has the opportunity to go 4 time units. Since P2's CPU burst is 4 time units, it's going to go for those 4 time units. Then it's going to go out to IO for 2 time units. It's going to remain a Q1, and it's going to arrive back in the ready queue at time 10 as a Q1. So now the current time is 8, and we have in our ready queue, we have P1, P3, and P4. And again, P1 is a level 2, and P3 got there before P4, so P3 is going to go next. And P3 gets the opportunity to go 4 time units, so it will go 2 only because that's how long its CPU burst is. And then it will go out to IO for 3 time units and come back into the ready queue at time 13. So next, the current time now is 10. And in the ready queue, we have P1, P2, and P4. And P4 is a level 1 that got there at time 7. And P2 is a level 1, but it got there after. So P4 is going to go next. Since P4 CPU burst is 5 time units, at time 14, P4 is going to get preempted. And it's going to have 1 time unit left of its CPU burst. It's going to go straight back into the ready queue at time 14, and it will be downgraded to a level 2. Now the current time is 14. In the ready queue, we have P1. We actually have all of them in the ready queue right now, so we only need to consider those processes that are level Q1. And we have P2, which has a CPU which got there first. So P2 is going to go until time 17, at which time P2 is going to be done and finished. All right, so now we are done with P2. P2 has completed all of its execution, and the current time is 17. And in the ready queue, we have P3, which is a level 1, and we have P5, which is a level 1. But P3 got there first, so P3 is going to go next and have the opportunity to go 4 time units. So P3 is going to finish at time 21, and then we have P3, which is also done. Now the current time is 21. In the ready queue, we have P1, P4, and P5. P5 will go, because it's the only one that's a level 1. It's going to go 3 time units until time 24. Then it's going to go out to IO for 2 time units, and it's going to remain a level 1 because it did not get preempted for time quantum, and it will come back in at time 26. Okay, so now the current time is 24. And in the ready queue, we only have P1 and P4, which are both level 2s, but P5 is out in IO, so we don't have to consider it right now, and P1 only has 1 time unit left of its CPU burst, so P1 is going to finish and be done at time 25, and then we have and go out to IO for 6 time units, and we'll come back to the ready queue at time 31. And then we have P4, which has 1 time unit left. P4 is going to go until time 26 and go out to IO for 2 time units and come back at time 28. And then we have P5, which is a level 1 and has now arrived at time 26. So P5 is going to finish at time 30. And so now the current time is 30. So you have to notice that both P1 and P4 are level 2s, but P1 is not there yet. So P4 is going to go first for its 7 time units, 37, followed by P1 until time 44. Now, once you get your Gantt chart done, and we can go back and see this is 100% CPU utilization, both shortest job first and first come, first serve, all took 44 time units. So once you get that done, you can go ahead and calculate the response times and the turnaround times and the wait times. So P1 has arrived originally at time 0, first got on the CPU at time 0, so P1's response time is 0. P2 arrived originally at time 3 and first got on the processor at time 4, so P2's response time is 1. P3 originally arrived at time 4, waited 4 time units before getting on the CPU. P4 originally arrived at time 7, waited 3 time units to get onto the CPU. And P5 originally arrived at time 14 and waited 7 time units to get onto the CPU. Remember, response time is a one-time measure from the first time that it arrives into the system to the first time it gets on the CPU. Then turnaround time, you go to the last entry, P1 finished at time 44, and you subtract the arrival time, which was original arrival time, which was 0, and P1 has a turnaround time of 44 time units. That's a 44. Okay, P2 finished all of its execution at time 17, arrived at time 3, so P2 should have a turnaround time of 14 time units. P3 finished all of its execution at time 21 and arrived at time 4, so it should have a turnaround time of 17 time units. P4 finished at 37 and arrived at 7, so it has a turnaround time of 30 time units. And P5 finished at time 30 and arrived at time 14, so it has a turnaround time of 16 time units. And you can add these 5 numbers up and divide by 5, and then you get the average. Also, that's the same with the response time. Now, to get the wait time, you could do one of two things. You could either take the total time. Remember that each process has a CPU time, wait time, and I/O time, and you add those together, and that equals the total time. So to get the wait time, you could just add up the CPU and I/O time and subtract it from the total time. So P1 CPU and I/O time is 18, and if you subtract 18 from 44, you would get 26 time units for P1's wait time. Or you could add up. So P1, you could add up the response time, which is 0, and then you would notice that P1 had waited 0 time units, and then P1 arrived again. The first time it arrived, it went back into the ready queue at time 4, and then it had to wait 20 time units before it could get the CPU again. And then it got back into the ready queue at time 31, and it had to wait 6 more time units. So you can see that you would still get the same result. So I'm not going to fill all that in. I will give you the results, but I will let you fill that in on your own. Okay, and we have one more algorithm to do, and this is preemptive priority. So this is not part of your CPU scheduling assignment. This is just another algorithm. And so what I'm going to do is I'm going to do preemptive priority in another video.